שמשוני.
אוקיי. טוב, נתחיל בשיעור. Let's start. Okay, thank you. Okay, so last week I started defining operators that we represent in second quantization, and in particular we defined one-body and two-body operators. And today I'm going to start showing you some examples of applying this formalism to more specific problems. And mostly we will give examples that come from electronic systems, where the system of particles is electrons, namely they are fermions. Okay? Good. So a reminder of the main concepts that we're going to use. First, we define a one-body operator. It's an operator that describes a physical quantity that acts only on one particle or on one particle at a time. So if it is applied on a state that has many particles, usually what it gives is just a trivial sum over contributions from each particle individually. Okay? That's a one body. And the most general form to write it is in the following way. You will usually have two indices, let's call them lambda and eta, of lambda. Here we have this matrix element of this operator acting on single particle states. A lambda dagger, A eta. Okay? And here the lambda and eta are indices that represent some quantum number. Okay? And the quantum number can be anything. It is some basis for the single particle states in terms of which we define our creation and annihilation operators. I remind you that in second quantization, the building blocks are that you have a set of lambda of some quantum numbers. Can be position, can be momentum, can be spin, can be harmonic oscillator index, whatever. But it's a basis, it's a complete basis for the single particle state. And then you can define the operators A and the A dagger in terms of this basis. And there is an algebra. I'm not writing it down again, but or maybe we do want to write it down. Let's not write it down, but you have it in your notebook many times. So it's a set of commutators or anti-commutators, depending on whether the fermions or bosons. And that's all we need to know. And all the states are Fock states, or can be written as a superposition of Fock states, which are states with well-defined number of particles. But we imagine working with systems with many, many particles, even a macroscopic number. So all the operators we want to be able to represent in this language. And once we do it, we know how to calculate expectation values or matrix elements in any choice of states in Fock space. Okay? Okay, so in this expression, I just remind that the matrix element is just a number. You can related to the lambda eta element of a matrix that describes this operator in the single particle basis. And if you choose a basis that is a basis of eigenstates of O, then you can eliminate one sum because this is diagonal. Okay? And then it becomes the simplest thing you can do. Okay, so this is a one body, and then a two body is most generally represented as a sum over 4 indices okay, and let me write it here as I want to use the notation. Yeah. Okay. And then we have A mu dagger, A mu prime dagger, A lambda prime, A. Okay, this will be our notation. So, and once again, this is a matrix element. Let me write more explicitly what it is. It is equivalently the matrix element between the Bryant-Ket states mu mu prime and lambda lambda prime. Or if you want, you can write it in terms of single particle wave functions in real space as a double integral over R and R prime of phi mu R star, phi mu prime R prime star, phi, sorry, then there is the operator, which I called O2. Two. Actually, I don't need it because once I write the matrix elements like this, you see it's not a matrix element with 2 indices. It's something that has at least 4 indices. Because I'm saying at least 4 because each of the lambdas can be itself split into 2 kinds of quantum numbers. For example, momentum and spin. Okay, we'll see it in the example that I'll talk later. So this is how, let me just finish the expression, okay? And these matrix elements are, as I said, are just complex numbers in general, which, given concrete expressions for the single particle wave functions, you can calculate, okay? And what this expression means is that you can think of it as a summation over many, many possible processes. Each process comes with a factor that determines its weight. And what this process, for each choice of the indices, what the process describes is something that you can draw as a simple diagram. I want you to get used today to some graphic language, because what is this process? you destroy two particles at states lambda and lambda prime and recreate them at mu and mu prime. This is in general. Sometimes you can have a situation where two of the indices are the same, but this is the general form. And quite generally, you can draw it as a diagram where you imagine that there are two incoming particles with quantum numbers lambda and lambda prime. Then there is some collision, some interaction, something that whose size is encoded by the matrix element. Okay? And then they come out as mu prime and mu. Okay? And when I draw these arrows, I don't know which, these are all identical particles. So all I care about is that all the information is in what quantum numbers I destroy and what I create. Okay? This is the process, yeah?
When you destroy, you take the vectors to meet the point.
Yeah, the vectors, just imagine, don't get confused because the quantum numbers are not necessarily momentum. I'm just thinking of it as conceptually as a process where two particles are sucked into the vacuum and recreated in some other state. That's one way to think. More simply, you can think of it as a collision process where they change their state.
It can be the same state.
If they are bosons, yes.
No, it's like they start from lambda prime and they stay after.
Of course, this will be, so this is a particular, of course, and this would be a particularly simple interaction where, where basically it's a product of the number of operators. But it's a special case. It's a simple special case, yes, of course. And you always have to remember that if there are fermions, then you cannot have any of the creation and annihilation operators cannot appear to power 2 or greater. Okay, it can only appear once, otherwise it's 0. Remember that. Okay, that actually simplifies a lot the case of fermions, which is the case that we're going to focus on today. Okay? All right, so these are all very general, and now let's get straight to an example. Actually, I understand from Sar that he started doing it in the tutorial, although I didn't get to it in the lecture yet, but let me just repeat it just from the start for a good measure, that everybody will be in line. Okay, so we are going to give to show you some examples of how to treat and how to use these notations for interacting electron systems. Okay, and actually when I say electrons, they don't have to be electrons, they can be any kind of fermions, but fermions is important. So this is an important property of the system. But why am I thinking about electrons? Because this is one of the physical realizations where if we think of properties of materials, most of the properties that are like electrical, magnetic properties of materials are dominated by the electrons, because these are the lightest particles, these are the most quantum particles in a solid state. Okay? And so if you want to understand material, solid materials, I emphasize as opposed to cold atoms or things like that, then the particles that play a role are electrons. And you can think of the ions or the heavier particles as some background potential in which the electrons are living. But one of the major problems is that electrons are electrically charged and they are interacting. And these interactions are very strong. In fact, it is actually not negligible, although they tell you, so most of you, I guess, already studied solid state, right? And they tell you that you can that some materials, at least like metals, you can treat the electrons as if they are free, and you get everything right. And that's true, but it's true for a very non-trivial reason. Because if you just look at the energy scales, the Coulomb interaction between electrons in a solid state, where the average distance between them is angstroms, is extremely large. It's not negligible. It's not a perturbation in the simple sense. Okay? All right, so I emphasize this because this is one of the formidable problems for which we need many body techniques to treat them, and especially if you want to study phenomena that are more complicated than behavior of metals. And the most interesting materials are not metals, are actually doing all sorts of crazy other things. Okay? So most generally, we want to, the problem we have to solve, let me first tell you what is the problem. If I'm writing the Hamiltonian of the system, it is divided to two parts, H naught and interaction. Okay? Yes?
What is the O and PE meaning?
Okay. Just getting to it. I just wrote an equation and now I'm saying what is, so H naught is the single particle Hamiltonian. Okay? Okay, so it's something that if I write it in real space, I can write it in terms of let me just assume here, okay, d dimensions in general. I can write it in real space in this way, where here the operator inside the, if you like, it's a local expression for the Hamiltonian operator. This is if I'm thinking of non-relativistic electrons, it's just the usual Hamiltonian of a single particle. Okay, it's a kinetic energy plus some potential, and these are psi and psi dagger are the field operators of creation and annihilation in real space, which I remind you, they are some generalization of the A and A dagger to the case where the index is continuous variable and they have units. And if I'm looking at fermions, and remember here we're talking about electrons, so psi and psi dagger create and annihilate electrons, their commutator is a Dirac delta and not a Kronecker delta, okay? Okay, but otherwise they have the same meaning as A and Omega. So this is one way of writing the H naught, but it's not a useful way to write it. Why? Because it's not diagonal in this basis. It never is. In real space, unless the potential, in some limit that the potential is huge, it's never a good quantum number. Okay? Mostly because you have kinetic energy, the single particle states are always better described in some other quantum number. So let us write it in its, sorry, I have to erase this to make space. Erase everything. Okay, so let me let me just leave it like that. But if I find the basis in which the Hamiltonian is diagonal, I'm talking now at the non-interacting, the single particle Hamiltonian, there is always a basis lambda where I can write it as a sum over lambda epsilon lambda a lambda dagger a lambda. Okay, and this would be a basis in which this is diagonal. And now, what is the interaction? The interaction energy usually, there is one thing, but one very important thing that I forgot when I wrote this. What did I forget? I'm talking about electrons. Very, very important. No. About the single, I'm talking about the operators. The operators psi, what is the problem with them? No. Okay, I'm missing something. I miss.
Psi.
Okay, so sorry, this is my mistake. I should start from it. So there is another index that I have to add if I'm talking about electrons. The space dependence is not the only degree of freedom. They also have a spin. And the spin is an independent internal degree of freedom. Okay, it's not something that is related to the space. It's another index. So what I really have to, okay, so to be more precise, I have to define the field operators psi sigma r. It's an annihilation of an electron at point r and spin sigma, where sigma can take two values, up and down, or plus or minus, and then you have the psi sigma dagger, the creation. And if I'm looking at the commutators, then I have to write it like this. The most general commutators will be that there is a Kronecker delta on the position, and on the spin I have, sorry, there is a Dirac delta on the position, and a Kronecker delta on the spin. Okay, so the spin is a separate degree of freedom that we have to carry, and if it's not electron, if it's a particle with some different spin, electrons have spin half, but there are particles that might have spin 3 or 3 halves, and then we have more indices. Okay? Yes?
You need to write sigma in this equation.
Yes, so that's what I just noticed that I wanted to say I'm missing. I have to put here the sum over sigma. Okay? And then it's fine. And now the lambda, actually the lambda is very abstract notation for a quantum number that can be a combination of, for example, if you have 3 particles in free space, the good quantum number is k, the momentum or the wave vector, and the spin. Okay? And now, okay, and now if I want to write a general interaction using these notations, I have to write it as a factor of 1/2 integral over r and r prime of, and now let me do it just a little slowly. So it's v of r prime, rho of r prime, but now the density, so v of r prime is just a potential that describes the interaction between the 2 particles. And rho is the density operator, which I want to represent in terms of the psi and psi dagger. But notice, because they have a spin, the definition of the density is, in fact, a sum over sigma of psi dagger psi. Okay, so in the density, or if it's just a total density, I actually have, if I'm writing this explicitly, it's psi dagger up, psi up, minus psi dagger down, plus, sorry. Okay, it's just summing the contribution of each spin. Okay, so I'm assuming that the basic interaction is between densities. Okay, you can also write interaction between the spin operators of the electrons, but usually this is not the microscopic origin. The origin is usually a density, but effectively you can write it in terms of spin. So let us assume that this is the general form of the interaction we want to account for, and this is the density operator. So if I plug it into this expression, I will have also a sum over sigma and sigma prime. Okay, I'm not writing it explicitly because it's long, but I'll have a double sum on the spins. And I will have 4 operators, 2 in annihilation and 2 creation. And there is another assumption that in many cases you can make. I wrote the interaction here in a most general way as something that depends on two coordinates. But if space is homogeneous, then usually the interaction between the two particles depends on the distance. Okay? That's only true if you have translation invariance, if you are in a homogeneous space. And we want to assume it usually for simplicity that the dependence on R and R prime is via the difference. Okay? So most interactions, most basic interactions are like that. So in that case, VEE is a function of only one variable, one space variable, which is the distance, the vector distance between two particles. For example, if the interaction is really Coulomb interaction, what is VEE? Let's write it down. So VEE of R, where R, as I said, this R here denotes actually the difference. Okay. How does it look? Coulomb interaction? Yes, it's E square over R. Okay. That's the function. Okay. No, so R is the argument, okay? Maybe I want to change notations so that you don't confuse. Let me just, okay. Let me just call it V, okay? Just call it V. Okay. Never mind, okay, you know what I mean, okay? I meant if it's one argument, it's just the distance, the difference between R and R prime. Okay, it's a function of one variable, and the variable is the difference. Yes? That's the definition of a density. If you just count what is density, the density is the number of particles per unit volume. So if you're just counting the number of particles, you don't care, you just account for all the degrees of freedom. Okay, you just count them. Because again, this is a function of a single variable. Okay, it's just a function. Okay? So this R is a dummy index that represents a difference. Okay? Okay, if you like, I can write it as a V of delta R. Okay. Clear? Okay? Okay, great. Okay, now, okay, so what I wrote here is very general, and now what is the problem we have to solve? We have a Hamiltonian, we have to solve a Schrödinger equation, right? If you like, we have to find what are the quantum states, what are the eigenstates, what is the spectrum of energy, what is the ground state. So there is a ground state and there are excitations. And I want to know the states, I want to know the energies. And usually, in fact, not usually, always, it's impossible to solve. Right? It's impossible. It's, impossible to solve analytically directly, an exact solution. Why is it impossible? Because we have a combination of a one-body and a two-body operator. even the simplest model we can write. Okay, there are some exceptions, I should say. There are some exceptions that some miracle happens. And in fact, almost all the exceptions are in one dimension. So in one dimension, there are all sorts of magical tricks you can play where you can solve exactly. Okay? And there are some very exotic models that you can solve even in 2 dimensions exactly, that of interacting problems. But usually, in the vast number of cases, it's impossible to solve. Okay? It's a very difficult problem. But what you can is, in some cases, you can find a simple solution to if you have only H naught or only the interaction. If one of the or the other is 0 or negligible, then maybe you can make progress. And in many physical situations, indeed, you can assume that one or the other is much smaller than the other and make an approximation using perturbation theory on the other. Okay? So the philosophy, and then you will see some examples in the next lectures and also in the tutorial that you can get a lot of rich physics by making such approximations. And although you didn't find the exact wave functions and exact energies, you already have a good description, a good enough description of what's going on. Okay? Okay, so I'm going to mention two limits where you can work with. One limit is when you know H naught, you found the lambdas, you know to write it in a diagonal form, and once you know to write it in this form, you also know all the spectrum and eigenstates, right? This is like an ideal gas of particles. You can solve it, but then if you want to do perturbation theory on the interaction, then you better write the interaction also in the same basis which you use for the H naught. Okay? And then you can do perturbation theory and we'll see how we do it. Okay? We'll make approximations, but first we want to find the quantum numbers of H naught. Okay, so this will be the first thing that we'll do today. We'll discuss the case that we have weakly interacting. This is the case where H naught, if I'm trying to quantify it, of course it's an operator, so it's not a number that has a value, but if I'm looking for typical energies, it's much bigger than the interaction. Okay, so the interaction can be treated perturbatively. So before we write it, let's express H naught in the basis in which it is diagonal. And I'll soon give you an example for electrons in a metal. And once, and these A lambdas A lambda and A lambda dagger, they are fermion operators. Okay, they are fermion operators. Therefore, what is the ground state? So suppose I have, now I'm telling you another information. This is my H naught. And before I treat the interaction, let me for the minute imagine what happens when interaction is 0. I want to find the ground state. And let me call it G naught, because it's the non-interactive ground state. But in order to be able to write the ground state, and of course I will write it in second quantization, I need one more piece of information. So knowing the Hamiltonian is not enough. You also need to tell me it's a many-body system, okay? There are many particles. So I need another piece of information, which is either what is the number of particles, or if you are in a grand canonical ensemble, what is the chemical potential? Okay? Now, as you know, and I think this is something you already learned in your undergraduate, for any system of fermions that have some kind of spectrum, okay, so these lambda states are, there's some spectrum of states, epsilon lambda 1, epsilon lambda 2, okay, and some of them may be degenerate because of the spin, but then I'm asking what is the ground state, and there is always a lowest, let's say there is a lowest energy state, otherwise there's a problem if it's not bounded from below. So what is the ground state? The ground state is the state with the lowest energy, the many-body ground state. Now I tell you that I have, if I'm working in a system with a well-defined number of particles, how do I get the ground state? What is it?
All of them in the same direction of the spin.
No, forget spin. I'm now more general. I have fermions. Yeah.
כולם מגיעים בדיוק על הסף של האנרגיית פרמית.
Right. Okay. So you already give me the answer for the case that there is a grand canonical assumption where there's a chemical potential, right? And that's the at 0 temperature. That's just a Fermi energy. Okay? Also, when you have a well-defined number of particles, you can translate it to E Fermi. Okay. So that's exactly right. So there is a Fermi level, and the Fermi level, or Fermi energy, describe the highest energy that you can occupy, and the ground state is a state where all the states below the Fermi energy are occupied, and all the states above are empty, right? Now remember, they're fermions, so they can only occupy one state. Each particle can occupy, each state can be occupied by only one fermion. Okay? So how does the ground state look like? It's a product of all the lambdas. Let me write it like this. All the lambdas that belong to the Fermi C, this set of occupied states, I can call a Fermi C. Okay, and actually, yeah, sometimes you can, I'll give it another notation in a minute, but the definition of this is that epsilon lambda is smaller or larger, smaller or equal to E Fermi. Okay, that's a definition of lambda belongs to F. Okay? And then this is how the ground state looks like. It's a product of creation operators, but only of states with lambda in small enough energy. And all of them acting on the vacuum give you the ground state. Okay? Yeah?
אנרגיה פרמית זה מה שלמדנו במצב מוצק.
Yes. The same.
איך זה הגיע לקוונטים?
Because solid state is described by quantum theory, quantum unibody theory. Okay? All right. I'm giving you an example that is based on something you already learned. Okay?
By what you write there, so you will have a system more than one ground state.
No. There is a single ground state.
Yes, but you have a lot of energy that is epsilon lambda.
No. So the ground state, it's a many-body ground state. Okay? It's a many-body ground state. It's not the ground state of a single particle. If you ask what is the ground state of a single particle, the answer is epsilon lambda 1. If you ask what is the ground state of two particles, it's when you have the two lowest energy, and etc. Okay? So actually, E Fermi is a parameterization of the number of particles. You know that in large number, it doesn't matter if you are in a canonical or grand canonical ensemble. E Fermi and the number of particles are related to each other. Okay? But that's a definition of a ground state, and
זה לא, אבל גרנד קנוני יכול להתווסף בחלקיקים, זה לא יכול בעיה. כשאני עושה את נגד פרמית שחלקיקים יכולים להתווסף לי פתאום מחוץ. הכל.
I don't understand the question. This is the ground state of a system described by this Hamiltonian and given a Fermi energy. Okay? Okay. Now you ask whether I can add particles. Sure. Now, if I act on this with an interaction, something is going to happen. Because okay, we'll discuss it later. But first, we want to understand how to describe the problem where I set off the interactions to 0, and then we'll write the interaction in the same language. Okay?
שזה מפריע לי פשוט זה משום שמגידה לי נגיד 2,000 חלקיקים או 1,000 חלקיקים, אז כשנגיד הייתי לוקח את הטמפרטורות 0, והפרט הייתי ממלא מספר מסוים של מצבים. אבל אם היו לי רק 1,000 חלקיקים, אז הייתי יכול למלא הרבה פחות מצבים, והייתי פשוט...
That's okay, so I'm saying that's very general. Now you can have 10 to the 23 particles, and this is the correct expression, okay? Okay? I'm giving you a prescription. Okay? You're right that many times the problem we will be interested in is when the number of terms in this product is 10 to the 23. Okay? And for that reason, we'll see how we deal with it. But I want here to introduce a useful, not a useful, but a convenient notation for a state like this, that is the ground state of non-interacting fermions. We will define it by the letter F, okay, where F stands for Fermi C. Okay? Fermi C. Okay? Why I call it a Fermi C? Because it's like an ocean filled with particles. Okay? And it can be filled by, in fact, if you have here a continuum of states, like if the states are described by a k vector in an infinite space, the number of states is infinite. Okay? And this is the ground state. Okay? And what are going to be excitations? There can be different kinds of excitations. I can add particles with higher energy, or I can take out a particle from the Fermi C and promote it to higher energy. This will have higher energy, right? And when we do so, we'll create a hole here. Okay, and the hole will also act like an excitation.
רגע, בהוספת חלקיק זה גם כן סוג של אקסיטציה מבחינתכם?
Yes. Anything that raises the energy is an excitation.
או אפילו אם הייתי לוקח חלקיק, לא, לעשות.
Okay? Yeah. Okay? Yes?
Can you repeat how we create that part?
No, we'll see it later. Okay, let's not jump ahead. I'm just saying that this is the ground state, and there are infinitely many states that are excitations of it. And what I define as an excitation is anything that has higher energy than this. And the energy of this, what is the energy of the state? What is the ground state energy, if you like? Can you suggest a simple expression? What is it going to be? It's very simple, actually. No. The states are, again, this is the Hamiltonian, okay? And I occupied all the lambdas until E Fermi. What is the ground state? The ground state is the total energy of the occupied states, right? Therefore, it is given by what? No, much simpler.
Summation of the energy until later.
Very good. Summation of lambda, again, belonging to this, of epsilon lambda, or if you like, by this summation, I mean I'm summing all the lambdas where epsilon lambda is smaller or equal to E Fermi. Okay? Up to all the epsilon lambda, up to E Fermi. Okay? So this is the ground state energy. Yes?
לא הבנתי למה ציינת בסוגריים מתחת לסיגמה.
This is to explain the notation. Okay, later I will stop writing it. Okay? That's what I mean by lambda part of F. Okay, it's part of the Fermi set. Okay, so this is so we know how to solve a single particle Hamiltonian for arbitrary number of particles. Now let's talk about the interaction. For simplicity, I'm going to assume that the interaction is indeed some potential of r minus r prime. This is the potential. Let me just call it V without the E because this is because it's going to be just a function. It's the interaction potential, where again for Coulomb interaction, Coulomb is just E squared over R. But R is not a good quantum number, so how will I write the more general expression for VEE? For the operator, it's 1/2 of a sum over lambda prime, lambda double prime, and lambda triple prime. Okay, I'm using now all the indices are some kind of lambdas of the matrix element of this potential in the basis lambda, which is lambda prime, lambda double prime, lambda triple prime, and it's defined the way I defined it in the beginning of the lecture. And now I have A lambda dagger, A lambda prime dagger, A lambda So this is how it looks. Generally, it can be quite complicated, depending on what is lambda. But now let's be more concrete and discuss interactions in a system where the single particle, the non-interacting part, is just free electrons. So a metal is, to a very good approximation, is a state of matter where the electrons, if you neglect the Coulomb interactions, they behave as free particles, right? So, so what are the quantum number lambda? The quantum numbers lambda, what are they? The good quantum numbers. They are the wave vector, right? And of course, sigma, the speed. Okay? So the single particle operators in which we are going to describe our Hamiltonian are A and A dagger of K sigma. Okay, they have two indices, wave vector and sigma. Now there's another thing that we know and that we need in order to calculate the matrix element of the interaction. Maybe I'll write on the side what is the definition of, so V lambda prime, lambda double prime, lambda triple prime is integral over space, double integral over space of the single particle wave functions. Okay, I need more space, sorry. I'll write it here. Okay, so it's an integral over R and R prime of phi lambda star R, phi lambda prime, R prime. Then I have V of R minus R prime, and what is this? Phi lambda double prime R prime, phi R. Okay, this integral is what we need to solve in order to find the matrix element in general. Okay. Now, in the case that lambda is just K and sigma, the sigma will appear in a trivial way, right? And inside the expression for the interaction, I will have a double summation over spins. But in addition, I have to know the wave function, the orbital wave functions of the space-dependent wave functions with the wave vector K. But we know these are free waves, right? These are very special types of states. So the real space dependence of the states, the phis that I have here is the subnormalization factor e to the I k dot r, right? They're just harmonic waves, right? Okay, and because of that, and I think You already did it in the tutorial, so I will not repeat the algebra. But I think you can easily see that if you plug in these simple exponents for the wave functions, and you do this integral, you find that first of all you get rid of one index. Why is that? Because there is, if the interaction only depends on the difference between, and there is actually translational invariance of the interaction, then there is momentum conservation. Okay? And the result of the integral will be nothing but a Fourier transform of the potential V of R. Okay? So let me show you what is the result. So in that case, first of all, let me write H naught, which is the single particle part of the Hamiltonian, can be expressed as a sum over K and sigma of epsilon K AK sigma dagger AK sigma, because the energy, the kinetic energy, doesn't depend on the spin unless you put a magnetic field, but let's assume we don't. Okay? So maybe there's a remark here that this is for zero magnetic field, because otherwise you have a Zeeman splitting of the spins. Okay, you know what I'm talking about, I hope. Okay, and what is epsilon K? It's a free energy. Right, it's exactly. Yeah, clearly. It's H bar square K square over 2n. Okay? This is what it is. And then later we'll discuss what is going to be the ground state in this case. It has a very nice construction. And now I want to write the interaction in the same basis, in the basis of the K's and sigmas. And because of the translation invariance that I mentioned, the final expression looks like this. I have a summation over K, K prime, and Q, only 3 momental indices, and 2 spin indices. The spin indices, why do I have only 2? Because, again, I start from a density. So each density operator is a sum of spins, okay, already. So, and then I have the following expression, V of Q, which I'll explain in a minute, and then A dagger of K plus Q and sigma, A dagger of K prime minus Q and sigma prime, A of K prime and sigma prime, K sigma. Okay?
What is Q?
Q is a vector that I'm summing off. And now I'm going to show you, I'm going to write, and I forgot to define what is VQ, V of Q. It's the Fourier transform of V of R. Okay, let me write it down explicitly. So VQ is just a Fourier transform e to the, I think it's correctly defined. Of V of R. Okay, and here there is some normalization factor that I'm not writing. Okay, it's a matter of definition. Actually, to be, no, let me just leave it like this. It's fine. Okay, so. It's just a Fourier transform of the function. So for example, if V of R is Coulomb interaction, E square over R, what is V of Q? Do you know? Familiar with this? I don't know if you've seen it, but in 3 dimensions, this is in 3D, if V of R is E square over R, if you compute its Fourier transform, you find that V of Q is 4 pi E square over Q square. Okay? Well, Q is the absolute value. Okay? This is true in 3 dimensions. But this is this is for the Coulomb interaction. I want to keep the interaction general. Okay, so let's not commit to what it is, and I want to interpret the result. Okay, let me put it in the box. And again, I emphasize this is a specific case where I write the interaction in the basis of momenta of electrons or particles with well-defined momentum and speed. Okay? Now, what does it describe? So, just as before, you see that here I get some kind of a scattering process because I annihilate 2 particles, one with momentum k and one with momentum k prime, and I create them with some different momenta. But what can you say about the momenta? Exactly, right. So it's like, if you look at the total, it's conserved. And the reason for it is, again, that I assume the interaction to be translation invariant, depending only on the distance and not on actual position. Okay? So if you like, it depends only on the relative variable and not on the center of mass, the relative position of the particles. That's why there is momentum conservation. And in this momentum conservation, there is, however, a transfer of momentum. And the momentum that is transferred at each process is Q. That's the meaning of Q. Now, if I want to plot it as a diagram, this is how it looks like. This is what I'm plotting now is a graphic interpretation of this expression. Okay? So what is going on? I have a particle comes with momentum k and spin sigma. It meets another particle with momentum k prime and spin sigma prime. And now they collide, and there is they emit a particle, or if you like, an imaginary, a virtual particle. This is embedded by the VQ. The VQ describes the amplitude for emitting such particle, but this particle carries momentum Q. Okay? And after the collision, sorry, I didn't draw it right. Let me redraw, sorry. Okay, let me do it. Let me do it here. I just this is not right. Okay. So again, there is an incoming particle with momentum k, an incoming particle with momentum k prime. They also can have different spins, but what happens at this point, this is of course just a graphic expression, is that this electron with momentum k or actually because of the way I've written it, let me think it like this. So the particle with momentum k prime emits a particle with momentum q, and because it emits momentum q, it's recreated with momentum k prime minus q. Okay, so there is, this is k prime minus q, and the spin remains the same because it's the spin didn't flip in this process. Yes?
So they emit a particle even before they collapse?
I mean, there's no before and after. It's all an instantaneous process. If you want to think of it as some scattering, so of course this is not the right way to think of it.
They
Because
need to bump to do it, or?
yeah, so what they need to, they actually, as you know, Coulomb interaction and many other forces, it's not a contact interaction, it acts from a distance.
So this is
And if we describe it here, we describe it in momentum space. So there's no information even about the position, but what we know is that the way this interaction can take place is if my electron with momentum k prime emits a particle, let me redraw it more clearly. It emits a particle with momentum q, which you can think of some kind of a boson, let's say a photon. In fact, if it's a Coulomb interaction, it is indeed a photon. It emits a particle, and this particle is being absorbed by the other electron. Okay? And therefore, the other electron is scattered with momentum k plus q. So this is what happens.
So the particle exchange between them virtual particles.
Exactly. This is exactly. That's the interpretation. That's the interpretation. That the way the force acts from a distance is that the two particles. The more basic process is that each particle with a charge, let's say, can emit a bosonic mediator. Okay? In fact, this mediator, and there are many of them in nature, the most familiar one is the photon, but you can also have phonons playing the same role, or the W boson and Z. They're called, more generally, they're called gauge particles. Gauge particles because there are some gauge fields. They're related to something that is like the photon. Okay, and the collision between two matter particles can be thought of as exchanging a virtual mediator, okay, a virtual gauge particle, and in the process, momentum is conserved, okay? So in momentum space, it's very clear that because one particle loses momentum q, the other gets it. And that's why the product has the same total momentum, okay? Okay, and this wiggly line is its weight, if you like, or its contribution to the entire process is embedded in the function v of q. V of q is not an operator, it's a function of q, but you can think of it as a matrix element that describes the probability, or more correctly, the amplitude probability for such a gauge particle with momentum q to appear. Okay? So as I said, there's a process where the particles exchange between them a gauge particle, let's say a photon, and V of q describes the probability for such photon to be emitted. Okay? Okay? It's, in fact, you can write it as an expectation value of some quantum operator related to the photon. But I'm not doing it right now, okay? That's more advanced. But I'm just explaining how you can interpret this, okay? Okay, so this is a graphic notation of what I wrote here in a formula. And we'll see, I hope we'll have some time for it later, not today, to see how using this graphic language, you can actually very easily get the answer for a calculation. Okay? It's very useful. Okay? At the moment, it's just a pictorial description of what I wrote in the formula. Okay? And this is an example for Feynman diagrams. This is what Feynman developed, among other things. Okay, very good. So we know how to write. An interaction in this basis, and we know also how to write the single particle Hamiltonian, and therefore we know how the single particle states look like. And what we would like to be able to do next is to say, okay, when I add the interaction, I can no longer solve the Schrödinger equation because the problem is not solvable exactly. So what can I do? Perturbation theory, let's say. Okay, because it's a weak, we are at the limit of a weakly interacting. What do you do in perturbation theory? One of the first things you do is to look for the correction to the energy, right? You remember what you do? What is the prescription?
כן, אנחנו מניחים קודם כל שאנחנו עובדים עם המילטוניאן כאילו הלא מופרע, משימים את המצבים העצמיים, ואז את הפרעה אנחנו לוקחים, נשים איזה הטלה, כאילו, את יודעת איך תצפית על הדבר הזה כדי לראות את ההפרעות בסדר ראשון?
Yeah, so if, for example, if you want to know the correction to the energy, you calculate the expectation value of the perturbation in the ground state of the thing, or in the non-interacting states. Okay, that's what you do. And you can do this calculation if you use this language in a relatively simple way. But notice that we have here something that on the first sight appears like a complication. What is the complication? So suppose I want to calculate the matrix element of this operator in a ground state that I'm now going to write explicitly. So this is now the ground state of H naught in our case, because the states are characterized by the free particle epsilon k. What is the ground state, which I call F? It's going to be, if I write it explicitly, it's all the k for which, and I'm writing again the definition, epsilon k is smaller than epsilon f of, and you also have a product of all the sigmas, AK sigma dagger acting on the vacuum. This is the ground state, right? Now, how can I write the condition on K more simply? Because remember, this is K is a K vector. The energy is a simple quadratic function of K that depends only on the absolute value of K, right? And therefore, and let's assume we are in 3 dimensions now. So K is a 3-dimensional vector, and there's a continuum of K states because we are in infinite space. And the energies are given by this kinetic energy. And all the Ks that appear in this ground state are the occupied states whose energy is smaller than E Fermi. Okay? Because the energy, so let's write it down explicitly. So epsilon k is given by this, and it has to be smaller or equal to epsilon Fermi. And because it depends only on the absolute value of k, I'm using throughout the notation. Okay, let's agree on this. Okay. So what can I say about the k vectors? If I want to plot the occupied states in k space. This is kx, ky, and some kz. Okay. How can I plot? How do the states look like in this space?
A sphere.
It's a sphere, exactly. So there is a so-called Fermi sphere in this case. Namely, it's a ball in K space with radius Kf, where what is Kf? It's the wave, the absolute value of K, which is related to E Fermi. Okay, so E Fermi is, you can write it as h bar square over 12 times a wave vector Kf, whose absolute value is Kf. And all the states on the sphere have energy that is exactly E Fermi, but the states that are inside, sorry, let me use blue color. So all the states that are inside the ball are occupied, and all the states outside are empty, okay? So this is the ground state of a free electron gas with Fermi energy epsilon, okay? So basically this is just all the K's whose absolute value is smaller than Kf. That's all. It's a ball. Okay, so this you already know. from your undergraduate. And now I want to pose a problem. And the problem is this. I want to take this interaction and compute the matrix element or the expectation value in the state F. Okay? So this is what I want to do in order to calculate perturbatively the correction to the energy from the interaction. Okay, so that's what I want to do in our case. I want to take VEE and calculate it. Okay. Now let's think of the calculation. I take an expression that is a sum over terms. Each of the terms has 4 operators. A dagger, with some indices. I apply it on the state F, where the state F is a product of many such A daggers acting on the vacuum. And on the other side, I have many A's acting on the vacuum. Okay? Now, what is the problem or the apparent problem? No, it's not. It's not. No, it's not 0. Okay, believe me. But the problem is there's a technical problem, an apparent technical problem, that it's complicated, right? I mean, we saw that if we have to calculate something like this, okay, let's say we have, I don't know, or a matrix element between, let's take something that doesn't vanish, something like this with some indices. Okay, something with 4 operators. How do you do the calculation? We saw it in class. You start using the commutators, anti-commutators, move them around until you get something plus something that has only annihilation operators, and A always annihilates the vacuum, right? Remember, this is a very important definition of a vacuum, or if you like, the definition of annihilation operators with respect to a vacuum is that they annihilate the vacuum. Okay? But now we don't have just 2 operators, 3, 4. We have 10 to the 12. In fact, we have a continuum of such things. Okay? So we're not going to start reshuffling. It's going to be very complicated. So I have an idea how to simplify things enormously. And this is the following thing. So we know that the interaction, if we just apply the interaction on the ground state, what can it do? I mean, and remember, it's weak interaction. It's just going to
Stretch.
What is actually, if we take just one term like this, each of the terms here, what does it do? It only acts on 2 particles, right? It annihilates 2 particles and recreates them in some other states. It's a 2-body. So it's not acting on 10 to the 23 particles. It's going, each term like this is going to do something only to a very tiny fraction of the particles inside the Fermi sea. So it's not useful to think of this whole thing and check each time what it does. No, what we want is to be able to define our ground state F, the ground state of the non-interactive problem. I want to define it as the new vacuum and define now annihilation and creation operators that are acting on it, and there will be only a small number of them that we need in order to describe the interaction. Okay? So, so let me start doing it and then we'll take a break. You understand the problem, right? I don't want to each time work with strings of millions of operations. I want to work with small number of two small algebra, okay? And I know that the physics is that applying the interaction on a Fermi sphere makes a very small effect in terms of how many particles are being affected, okay? So I want to define new annihilation and creation operators in such a way that the state F will redefine our vacuum, okay? So I'm just stating the goal, and we'll do it after the break. What I want is to define now new annihilation and creation operators. I call them CK sigma instead of A, C and C dagger. I give them new names in such a way that CK sigma acting on F, not on the real vacuum, is 0 for any K and any sigma. Okay, that's what I want. And in terms of them, I'll rewrite, of course, the interaction in terms of them, and that will simplify my calculations in all this. Okay, so we'll do it after the break. Let me see if there was some final decision. Okay, that's like okay. So now I want now to show you a trick that is going to be useful, as I said, when we talk about systems of many particles. We want to account for the fact that each time we apply the interaction on the ground state of the non-interacting problem, it only changes the state of very few particles at a time. So we want to do, let me first make one exercise. I want to check if I take the Fermi C and I apply on it an annihilation operator, okay? Will I always get 0? Or actually, will I get, in which case I will get 0? Okay, let me put it this way. Okay, so let's check. Let's see what it does. So what is F? F is a product over all the K's and all the sigmas, and let me give them an index K prime and sigma prime because I want to distinguish it from this particular K and sigma. So these are just dummy indices, and I take the product of all the K primes and the sigma primes, a dagger, and I apply it on the vacuum. Okay? What am I going to get? Let's see. So how do I do this? In order to check in which case or whether it annihilates the state, I have to move the annihilation operator to the right, right? And before I do that, I want to rewrite the product in such a state. Remember, the product is not over all the K prime and sigma prime, but only provided that K prime belongs to F. Okay? All right, so so now let's check the case where K itself belongs to F as well. Okay? Let's assume that K belongs to F. I apply it on this state. So this is K prime belongs to F and sigma prime. And K prime sigma prime acting on the vacuum. And because K is actually one of these K primes, right? Because it also belongs to F. I can rewrite the product as a product of all the K's that are different from K times a K. A K sigma prime. Okay? Okay, and that is acting on the vacuum. So, okay, so somewhere in this product, I have K primes that are different from K, and only one of them is equal to K, but it's not necessarily here on the right. It can be somewhere in the middle. So when I'm going from this form to this form, what happens? I pick up a minus sign to the power of how many permutations I needed to bring it to the right. Okay? Now I know for sure that actually, let me also put the sigma to be the same, because it has to be exactly the same quantum number. Okay, otherwise I'm not interested.
What
So-
do you do? Massive person?
So, okay, sorry, I'm doing it a little. You know what? Let me not do it in K-space. I want to do it more general with some quantum number. And then you remember that this quantum number can be K and sigma, okay? Just to simplify the notation. So, sorry, let me do it again. So I have a state, a Fermi C that I write as sum over as a product of lambda belonging to F of a lambda dagger. Okay? And now I'm applying, I take some, let me also denote it like this to avoid confusion, and I'm taking some particular lambda inside F, and I apply a lambda on F. Okay? And I want to see what is the result.
Just when lambda is part of F, lambda is not part of F.
Right. So at the moment I'm choosing it. I will do the both cases. Okay. So the first thing I do is to take lambda to be part of F. No K.
No, okay.
I replace the. I don't want to have both K and sigma because it complicates. Okay. I have one index. This index includes the K's and the sigmas. All right. Sorry for the. I mean, I wanted to go straight to the Fermi ball, but it will be simpler to do it like this. Okay. So in order to be able to do the calculation, I divide the product in here to all the lambda primes that are different from lambda, and there's only one lambda prime that equals lambda, okay? And the one that is equal to lambda, I reshuffle it with all the others, so it will go to the right, okay? Okay, and when I do this, I pick here some minus sign to the power p, where p is some permutation, okay? Now I don't really care about this, because it's just a phase factor, it's just either plus or minus, okay? And then I have lambda, a product over all the lambda primes that are different from lambda, times a dagger lambda acting on the vacuum. You agree, right? So here I just did some reshuffling. And now I do another reshuffling because I want to bring this this A of lambda, I want to pass over all the lambda primes that are different from it, because I know that when I do this, I always pick just a minus or plus sign, okay? All right, so this is what I want to do, and it will give me minus p minus to the power, let me call it p twiddle with some other permutation. And then I have a product of lambda prime different from lambda of a lambda prime dagger times a lambda dagger active on the vacuum. Okay? Yes?
What is minus means?
It means what I'm doing in order to reshuffle, when I reshuffle operators that are all different quantum numbers, right? So the commutator or anti-commutator never give me a 1. Okay? Then I'm picking, each time I do a permutation, I pick a minus sign if there is an odd number or a plus sign if it's, okay? Now I don't care, I don't know what is p, I don't know. It's either odd or even, but I also don't care.
But it's minus 1?
It's either minus or plus, but I don't care. Because the question I ask is whether this is 0 or not 0. That's, okay, I'm asking the question whether it's 0.
Okay.
So I don't care about it. Okay?
רוצים פשוט להעביר את אופרטור ההשמדה זה כל הדרך לצד ימין.
Exactly. Let me put it, I want to do two things. First of all, out of the many lambda primes, I want to cherry pick this one lambda that I'm interested in here and reshuffle it to the right. Second, I also want to reshuffle the operator applied from the left and bring it to the right, okay? So it costs me 2 phase factors which are unknown and are unimportant.
את רוצה להעביר את ה-A דגר המתאים גם כן לצד ימין לצורך העניין?
I don't have to, yeah, this is a dagger. This was not necessarily on the right. It was somewhere, okay, I had a lambda 1, a lambda 2, a lambda, and some other things, right? Now I want to move this here. I don't know, I have either odd or even number of operators, but that's all. I just pick either minus or plus, I'm not committing.
האופרטורי הבנייה, כל האופרטורי הסולם העלה הם חילופין?
Of course, because there are different quantum numbers. There are fermions, remember, fermions. Okay, there's one of each.
ואז כאילו את אומרת
No problem.
אפס כשתשים?
Yes. No, the commutator is always there. It's always 0. It's always. Okay? Therefore, I always have that a lambda dagger, a lambda prime is minus a lambda prime. Okay? There's no 1. There's no one.
אז למה יש לנו פה עוד פעם שני מינוסים?
Again, I did two permutations. Okay. Okay. Let's go on because we, you know. Okay. Okay. So. Okay. You agree to this. Okay. Now let's see. Now this. Now, unfortunately, there is a one. Right? So this equals 1 minus a dagger a. The second term will indeed annihilate the vacuum, but I am left with the 1. And therefore, it's not 0. What actually I get if I do this? When I apply annihilation on a state that already has the lambda occupied, what am I doing? I get a new state. Let me now erase the line here. This result is up to, again, the phase factors, which I don't care. It's a product of the lambda prime that is different from lambda. Okay. How does this state differs from the original Fermi C? It has all the states occupied except one, the one that has lambda prime equal lambda. In other words, it has a hole. It has a hole because, and that's exactly what happens. The annihilation operator, when I apply it on, I have all these states occupied. I apply annihilation operator on a state that is already occupied, and I create a hole. Okay. Okay. So this is not doing the. This is actually not annihilating F, meaning that for the state F, A lambda, when lambda is inside F, is not a vacuum, okay? F is not the vacuum of it. Okay, it creates a particle. This particle is a hole, in fact, in the Fermi C. Okay. On the other hand, now I take lambda not included in F. Let's say some excited state that is above the Fermi level. And I apply the annihilation operator. What will I get then? I'm not even doing the calculation. The calculation is the same. I have to reshuffle, but
0.
then I get 0. Why? Because I bypass all the lambda prime different from lambda. And that's it. Right. So this gives me 0. Okay? Okay. But fine, that's sort of trivial. Okay? That's sort of trivial. But I want to show you something else that is a bit less trivial. And that's the following. If I now take lambda that is inside the Fermi C, okay, and I apply a lambda dagger on F, what will I get?
Create another 0.
I create another fermion in a state that is already occupied.
Yeah.
What does it give me?
0.
0. Exactly. Because, and if you want to see the calculation, once again, I will have some phase factor times a product of all the lambda primes different from lambda, a lambda prime dagger, times after all the reshufflings, I will have a lambda dagger square, and that's 0. Okay? So I have actually two ways of, let me write it down here. and try to summarize it. If lambda is inside the Fermi sea, okay, then if I apply a creation operator, I get 0. On the other hand, if lambda is not in the Fermi sea, the annihilation operator gives 0. But in both cases, I get 0. Okay? So I have now a way to define a new operator, a new annihilation operator, in such a way that it's either A or A dagger, depending on whether lambda is inside or outside. Okay? So let me define it. And we'll call it, we denote it by the letter C. C lambda is defined as A lambda for lambda not inside F, and A lambda dagger when lambda is inside F. Okay? It's a definition. Another way to write it is if I define here, I can define a theta function f lambda, theta lambda f. I define it to be 1 when lambda is inside f, and 0 otherwise. Okay, that's a definition. It's like the theta function, but in the space of the quantum numbers lambda. And with this theta function, I can rewrite my my operator. And let me write it here. So C lambda, I can write it as theta f lambda of A lambda dagger plus 1 minus theta of A lambda. Okay? Okay, and this definition of C, when it acts on the state F, the full Fermi C, always gives me 0 for any lambda. Okay, and therefore, by the way that we define a vacuum and annihilation operators, it is an annihilation operator with respect to F. Now, what kind of form does it have? It's you can think of it as a superposition. It's a trivial superposition, but still, it's a superposition of creation and annihilation. Okay. Now, later in the course, in 2 weeks or so, we're going to see a less trivial example where where you can define such particles, and this is called the Bogoliubov transformation, that are non-trivial superpositions of A and A dagger. Okay, and that's something, it's like a combination of an electron and a hole, particle and an antiparticle fluid. Okay? Now, why is I'm saying that this is trivial? Because the coefficients are either 0, 1 or 1, 0. Okay? Because the theta can only take values 0 and 1. But if it could take some arbitrary value, it could be really a superposition. Okay? But for the problem that we have, the ground state that we have here, which has a well-defined number of particles that are occupying the sphere, or the Fermi sphere, Fermi C in general, these are the elementary operators that act as annihilation, and of course we can define a creation operator. What will be the C dagger?
Yeah.
Just by definition, it's the Hermitian conjugate of this. These coefficients are real, so it's theta lambda f of A lambda plus 1 minus theta f of A lambda dagger. Okay? And this, with these new building blocks, we can do the same mathematics that we are used to with the A's, because you can trivially convince yourself, I'm not even bothering to prove it, that this transformation from AA dagger to CC dagger is obeying that the anti-commutators of the C's are exactly the same as the A. They are canonical commutators, anti-commutators, sorry, because they are fermions. So these are 0, and C lambda prime dagger is a delta of lambda prime. Okay? You can very easily convince yourself that it's true, I think. If not, think about it for the night, okay? So it preserves, this is a transformation that preserves the commutators. In other words, it's a unitary transformation. And now, why is it useful? Because, as I said, you don't need to work with the huge string of operators that is embedded in the definition of F. Because in terms of the C's, this is now a vacuum. Okay, this, if I'm now back to the case where lambda is equal to K and sigma, then the quantum numbers, the states that are filled are all the states in the Fermi ball. And if I'm applying an operator that includes a small number of A's and A dagger, I can convert them to C and C dagger. And in terms of the C, I already treat it as a vacuum. Okay? So I once again do a calculation with 1, 2, up to 4 operators in that sense. This is the trick. Okay? In particular, let's go back to the interaction that we wrote here. So when I expressed it in terms of A and A dagger, notice that it's a product of 4 operators. But there is another way to write it, which, if you think of it, is very intuitive, and we could get to it directly. And this is the following. I now let me write it here. I don't know if you need this. Okay, let me just, for good measure, I will write the definition of theta here. This is just for good measure. Okay. So, I remind you that we defined a density operator for the electrons to be a sum over sigma of psi dagger r sigma psi r sigma. This is the density in real space. Now I can make a Fourier transform of it, right? What will be the Fourier transform? I call it rho Q. It's an integral over R of e to the minus I Q dot R times rho, right? That's a definition. And now if you express rho in terms of the psi's, and remember that each of the psi is a sum over Fourier components, and the Fourier components are nothing but the AK sigma dagger and the AA. Then I think this may be in the homework exercise. You can convince yourself that rho Q can be written as a sum over K and sigma of A dagger K minus Q sigma A K sigma. Okay? Just do the calculation, or you will have to do it in one of the homeworks, I think. And okay, this is just a result of the calculation. So notice that what is the meaning of rho Q, first of all? It's a Fourier component of the density operator, and you see that it's not given by just one product of A and A dagger, right? It's actually, in K-space, it's not local because it involves momentum transfer. Now, what is this process describing? This is a one-body operator now, right? That is expressed in a basis that is not diagonal, okay? And therefore, it describes like hopping in momentum. And what does it describe? Let's go back to the picture because it's very intuitive. If you take an electron at state K, you destroy it and recreate it at the state K minus Q. Okay? Now, so this is what it does. It takes somewhere in momentum space. For example, if I apply it on the states outside the ball, it does nothing because it's empty, right? If I do it on states inside the ball, both of them, K and K minus Q are inside the ball, then what does it do? In fact, it's not necessarily zero, but it will not do anything. It will just exchange two particles that are identical anyway, right? So it does nothing. Exactly. So the only non-trivial effect it can have is if it acts on if K is inside and K minus Q is outside.
אם את עושה K מינוס Q והיה שם כבר חלקיק שהיה לפני כן בפנים, אז הוא אמורה להשיג שני חלקיקים באותו מקום, אז הוא אמור לאפס את זה.
No. If one of them, if K is inside, then AK, remember, it's not annihilating. It's annihilating it, creating a hole, but then it recreates a particle outside. So let me describe it in a picture, okay? So inside the ball, you have some K that is inside, it's K smaller than K Fermi. And okay, there's a minus Q, so let's let's define Q to be a vector like this, doesn't matter. So let me call this the red spot. This is K, some K, and K minus Q is here.
זה וקטור שמגיע לנקודה.
This is K minus Q, where Q, these are 2 points in K space, okay? And Q, what is Q? Q is this vector, okay? So this is, if I define Q to be this is Q, okay? So when I subtract Q, I get outside of the ball. Okay? Okay, so when I apply this term of rho Q on the Fermi surface, it creates an excitation. What kind of excitation? It creates a hole in K and a new particle outside of the ball. Okay? And this kind of excitation, it's called an exciton. Okay? But basically, this is it. And these kind of processes are what is going to contribute to a non-trivial contribution from the interaction. Okay? So when we calculate expectation value of the interaction in these kind of states, we have to account for this kind of processes, and we'll see later, and I think it will be only next week, what it does, but the principle is this, that if I'm now rewriting them in terms of the new operators C and C dagger, I can replace this A and AK and AK minus Q by their respective C's, and notice that then in this language rho Q can be re-expressed as a sum over K and sigma of C dagger K minus Q, C dagger K, okay? 2 daggers, okay? Where, and this will give me something non-trivial every time, because the C dagger is either A or A dagger, depending on whether K is inside or outside. And every time that acting with A gives me 0 is anyway not accounted. Okay, it's not something we have to account. So we can actually represent the density operator in this language by a sum of processes whereby you always create excitations. And in the excitations, each excitation includes 2 fermions. Okay? One is a hole, and another is a particle. Okay? And therefore, the combined excitation, which is what we call an exciton, is a boson. Okay? It's a product of 2 or even number of fermions. If you think of it as one object, that's a boson. Okay? It says, yeah, okay.
Efrat,
Yes.
you said that if both K and K minus Q are in our ball, we don't care, but
Right.
if they are fermions, we do care if they switch places.
Yeah, I mean, you get a minus. But a state is always defined up to a global phase. So that I don't define it as a new state. Okay? It's important to keep in mind all this phase factor, global phase factor, is not important. Okay? Yes.
למה זה בוזונים, אקסיטונים?
I'm actually not proving. Okay, that's actually a good question, because in order to prove that this object is a boson, I have to prove to you that it obeys bosonic commutations. Actually, it does only in some approximation. I'm not going to show it, but this is actually something I had to cut off the course. I'm sorry for that, but but it's actually not clear. I'm just saying it has the potential for it. And the reason it has the potential is that it's a composite object of two fermions. And if you think of it, if you have two fermions and a two fermion molecule, if you exchange it with another two fermion molecule, the minus sign changes twice and it becomes symmetric instead of anti-symmetric. If you think of it in first quantization. Yeah, the whole and the particle are both fermions, okay? But an even number of fermions, when you exchange them, creates a plus sign. Therefore, it's a bosonic thing, but you are right that it's actually not exactly a boson. You need to do some to make some assumptions to get something that I can identify as a well-defined boson. Okay? Mm-hmm. But what I'm saying is that it's an operator. Instead of writing the interaction like this with the A's and A daggers, what I can do, and you can with some algebra you can convince yourself that this expression is equivalent to the following expression. You sum only over Q, rho Q times rho minus Q. Okay? And if you plug in the definition of rho in terms of the A's and A daggers, you can convince yourself that this and this are one and the same. Okay? So very simple. You see, the interaction is nothing but a product of density operators. By the way, there's something I forgot to mention, and we have already seen it. Rho of R is a density operator. It's a Hermitian operator. Therefore, what can we say about its Fourier component? Remember? It's not Hermitian, but it does obey some property that we have seen. Remember, Remez, the phi of R and phi of K, it's the same thing. Hermitian operator, if its Fourier component, rho of Q, is rho dagger of minus Q. Okay? So actually, what I wrote here is like rho dagger, rho Q. And therefore, actually, it's very tempting, right? If I write it like this, okay, so this is actually like the same as writing rho dagger Q, rho Q. It's very tempting to say, oh, rho is some boson with wave vector Q, and VQ is just its energy. But it's not always true. It's true in some very particular cases. In one dimension, you can play this game in a particular model. Okay, it's not always true. But it would be very nice if it's true. Okay? Good? Okay. But this is, I mean, of course, except the fact that it's not really obeying a bosonic commutation, this is the form of the interaction in general. Okay? All right. Okay, so later on we are going to see how we use all these tools to compute matrix elements and so on. But now I want to move to another example. So up till now, what did I do? I looked at a particular case where I have a weakly interacting particles. H naught, the non-interacting part, I solved. Okay, I solved, I know the spectrum, I know the ground state, everything is solved. And now I want to add the interaction as a perturbation. Okay? But I can have an opposite situation, and in nature there are many examples for it, that the total Hamiltonian H naught plus V, the V electron-electron interaction is much bigger than the H naught. Okay? And example of that you can find in, once again, if the example is a solid state, electrons in solid state, you can find it in cases where you have some insulating material where the non-interacting electrons are tightly bound to lattice sites in a crystal. Okay? And in fact, this is why these materials are much more interesting than metals. Metals are really boring. I mean, they're just gas with some interactions can be treated perturbatively, and you don't get new phenomenology from that. But if you have a situation where the kinetic energy of the particles is small, nearly zero or negligible, and all you have is in the interaction, then it opens up a rich set of possibilities, and it can create new states of matter, magnetism, superconductivity, charge density waves, all sorts of structures where you have some non-trivial state of collective state of matter, and it's dominated by the interaction. Okay? So in order to describe this limit, let me now erase all this. Yeah?
I'm not sure if I remember correctly, but isn't the rho Q should be, the Q, rho Q dagger should be rho minus?
Well, you can always put the dagger.
Yeah, and it doesn't, okay.
It's the same. Yeah, you're right. Yeah. Okay. Just go from Q to minus.
Yeah, okay.
Okay? Yeah, so rho Q dagger is putting plus.
Yeah, because I remember we wrote it like the other way. But
yeah, but yeah. You agree that it's the same. Yeah. Okay, good. So we are going to the second example, the second type of problems. And this is interactions in let me call it a tight binding basis. Let me just verify. So all of you took a solid state, right? In undergraduate, you know the tight binding approximation. If you don't, never mind, it's not crucial, but I can, in one sentence, explain what it is. So if you have a crystal where the electrons are not, now I'm forgetting about interactions, just describing the atomic states. So in a solid material that is not a conductor, a better description of the basis of wave functions for the electrons is that are almost tied to the atoms. Okay? So they sit in a small environment of the atoms. The wave functions are localized on lattice sites in a crystal, and because they are still wave functions, they have a width, they overlap, that's why you have some kinetic energy. Okay? But it's relatively small. So it's the opposite approximation of what we do in a metal. And the quantum number that is convenient to work with is not the momentum K, but it's the lattice site in a crystal. Okay? So that is usually the situation where you have a crystal with some order, and there is an index I that denotes the lattice site. Okay? And the wave functions are looking something like this. Okay, so the lattice sites are located in some positions Ri that are ordered in an array, very ordered array. And the wave function looks like this. It's localized near the atom, near the lattice site. Okay? So if I want to write a general Hamiltonian describing electrons in such a system, and I first write the H naught, okay? How does it look like? You can write it generally as a sum. There is another thing that there are bands, okay? In solids, you know, the energy spectrum are bands, but let us assume that all the bands, except for one, are completely filled and don't play a role, so I don't write a band index. Then you have something like that, and you have some epsilon, let me write it like this, sum over I and sigma of A dagger I sigma, AI sigma. This epsilon is an on-site energy. It describes basically more or less the atomic energy, okay? And plus a sum over I and J. If you like to be more precise, I different from J. I different from J. There's some coefficient, Tij, AI dagger Aj, plus the Hermitian conjugate, which is Tij star Aj dagger. Okay? And these T's are they can be complex numbers because this combination is Hermitian. These are the two kinds of terms that you have, and I and J can be any two sites. Now, what this model describes? Let us look. So, as I said, the first term is trivial. Okay? Actually, if you look at this operator, what is this? Okay, so each of the terms is a number operator of electron at site I at spin sigma. If you sum over all the i's and all the sigma, what do you get? Just the number, not okay, without the epsilon, just the sum over. This is just the number the number operator. Okay? So in fact, the first term is not so interesting because it's again like a reference energy that with tuning of the chemical potential, we can set it to 0, or we can treat it as a reference 0, okay? But the second term is very important because it actually encodes the kinetic energy. What does it describe? So TIJs are called hopping coefficients. Why? Because they describe hopping from site J to I or vice versa. Okay, so pictorially, the process, this operator, I have a site I and a site J. They are like two atoms. And this describes a process whereby, sorry, I forgot the sigma. Sorry about that, but the sigma, because these processes are not changing the spin, they're just describing kinetic energy, okay? There's some probability or some amplitude for particles to hop from site to site. Okay?
So you also summing by sigma.
What?
The summation is also for sigma.
Yes, the summation, yes, you're right. Yeah, there is a trivial summation over sigma, both here and here. Okay, sure. Okay? Okay, now, of course, the Tij depend on the distance between the sites. And if the wave functions really look like this, and there is a very small overlap between them, then in fact, they're exponentially decaying with the distance to such extent that we can make an approximation and keep, let's say, only the nearest neighbors, or in some cases, you better account for the next nearest neighbor because they may have a non-trivial effect. So a simplified version of this, which is like, this is called a tight binding. It's initials of tight binding. Approximation. It's an approximation of this. Has only the first term, and the hopping term is embedded by one okay, and this runs over all the i's and j's, so yeah, it looks like this, plus and here I actually chose t to be real. It doesn't have to be, but in the simplest model, it's just one parameter. Okay, don't confuse it with time. It's not time, it's t. It's a parameter. Okay, for tight, never mind, I don't know, but this is the standard notation. You are familiar with this notation? It's nearest neighbors. Okay, when I put these angular brackets, it denotes nearest neighbors. Okay? Good. So this is called the tight binding model. And notice that I'm not using here a basis where usually I said it's useful to write the Hamiltonian where H naught, at least the easy part that we can easily solve, is written in its diagonal basis. Here I don't want to do it. Why? Because it turns out the H naught, this H naught is not going to be the big, it's going to be the smaller part of the Hamiltonian on which we make the perturbation. So I better choose a basis that is convenient for the interaction, not for the free part. Okay? And in the free part, the important term is the hopping, because the first one is just constant. Okay? And you'll see it actually in the tutorial of next week, how such a hopping can give you wonderful things, okay? Okay, but first, let us talk on the interaction. So I chose this basis because I said it's convenient for the interactions. And what I'm going to do now is to classify the important interaction terms, okay? Yeah.
טייט ביינדינג זה השם של הקול או שזה השם של
It's the name of the choice of basis. Actually, this kind of wave functions are called Vanier function. And they are the Fourier transforms of the Bloch functions. All that I'm not even writing because it's out of the scope of this course. But it's the tight binding approximation is an approximation, which neglects all the higher Hopik terms. But the basis, the choice of basis, is a basis of localized functions instead of free waves. It's the exact opposite of the free wave, okay? There are nearly delta functions on the site.
החלק המרכזי זה המינוס סטיק הפרס. זה בעצם החלק.
That's the interesting part, but once again, this part is, T is small, okay? We're going to assume that there is some energy scale for the interaction that will denote by U, and U is much larger than T. That's the limit we would like to work with, okay? All right. So, classification of interactions. So, interaction terms. And what I'm going to do is, first of all, I'm writing the most general interaction term. And it's just, we already wrote the most general form in the beginning of the class, but now I want to use the basis of the site, the lattice site basis. So it's going to be of the form 1/2, and now I have a sum of indices I prime, j prime of u I prime, j prime, and then ai dagger. And then of course I also have a sigma and sigma prime, the spins, a sigma, ai sigma, a dagger I prime sigma prime, a j prime sigma prime, a j sigma. Okay?
Why do we have also sigma prime?
This is because once again it's an interaction. It's density. Each density is a sum over sigma. Okay? That's always true. No matter what is the basis for the orbital degree of freedom, the spin appears in the density always as a sum. Okay? And that's why you always have a sum of 2 indices of the spin. In one body it's a single sum, and the 2 body it's a double sum. Okay? Okay, good. And now I can also write what is I prime, j prime. What is the definition? It's if I once again want to write it in real space, I have to look at what are the wave functions R and I prime star, and then I have then I have the interaction, which once again it can be Coulomb interaction or whatever. And here I have, what is it, j prime and j of r. Okay? And these are all vectors. I have to write them. Never mind. This is an integral you have to solve to find the matrix elements ui I prime, jj prime, and in principle there can be some result for any choice of the 4 indices. But remember what kind of wave functions they are. They are very tightly localized on a site. So what is going to, there is going to be some hierarchy of coefficients here. Not all the interactions are equally strong. Which interactions will be strongest? Nearest neighbors, or even a single on-site. Remember, we are allowed to have an on-site because we also have the spin. Okay? But one thing is sure that the farther are the indices, it's going to decay exponentially and to the extent that we probably can neglect much of them, except for up to yes. Okay? And of course, in some cases, you have more complicated lattices where inside the unit cell you have different atoms. Then you can have, but it's an order 1 number of neighbors. That's all. And all the others we can throw away. So we are interested in very particular choices of this general interaction, okay? And I'm going to classify them by different names. Yeah, there was a question?
Yes. צריך להיות B ולא U.
So it is, this is again just a matter of the culture of the subject. In this kind of problems, when you work with tight binding, you call the interaction U and not V. Okay, that's just a culture. I'm getting used to what you see in the literature. If you open a book, and often in this limit, it's convenient to, it's not convenient, it's just a convention. That's all. Yeah?
השפעת הגרעין על האלקטרונים, לפי השפעת הגרעין, אז האלקטרונים מחוברים לגרעין.
No, that's why, so that's what causes causes the wave function to look like. If the lattice, now it depends on the lattice structure, but you know, in a lattice like diamond, okay,
איפה רואים את זה בתוך הפוטנציאל, בתוך ה-U עצמו?
No, sorry. Let's make a statement in the beginning. So, the story of the ion, the nucleus or the atom where the electron lives, that's part of H naught. It's not interaction because we are not interested in the protons. Okay. We're interested in the electrons, and for them, the protons or the ions are background potential. They define a periodic lattice. That's why you have band structure, you have Bloch states. All that is accounted for in H naught. Okay? That's a single particle. It's a single body potential. VR prime is the interaction between electrons. Electron-electron interaction, okay? Like the Coulomb interaction, essentially, okay?
איך אבל נתחיל של אינטראקציה של אותו מקום, אותו מקום בגלל הספין? של אותו מקום?
Wait, we'll see. Okay, but first of all, this is just a definition, okay? And here I have everything, but among the many terms that I have here, I want to distinguish actually 3 important ones. Okay, and this is what I'm going to introduce to you now. Okay, so the first type of interaction terms, I'm going to call it Hartree terms, or sometimes we call it direct. Hartree is named after a person, okay? What are they? So, among the many matrix elements that I can define here I have 4 indices. Like I can choose 2 of them to be the same, okay? So, the Hartree terms are terms where there is an ij and another ij. Okay? And because it depends only on 2 indices, let me give it a name, Vij. Okay? Again, it's a particular, out of the many I prime, JJ primes, I choose particular combinations where actually, here I change the indices, but I have I prime is J, and there is I and J. Okay, just 2 indices, yeah?
But to say U and V, it's not the equivalent.
No, this is a definition that is only relevant for this, for number 1. Okay? Okay?
Is it the same on the Hartree?
If you like a different name, if you don't like the V, let me call it H is for Hartree. Okay? Okay. Now, what is special about them? So first let us look at the relevant matrix elements. So what is this? If I write it explicitly, you see that it's a double integral of phi I of R, sorry, let me just, yeah, phi of R, phi J R prime, V of R R prime, and now I have, sorry, this is a star, and now I have, once again, I have J R prime and phi of the same I, okay? I just copied the definition, but notice that what do I have here? Phi I R times phi star of the same I is nothing but phi absolute value square. So I can write it like this. So it's actually phi I of R absolute value square times absolute value square of phi J of R prime times the interaction potential. Okay, this is what it is. So it basically just, these are all positive numbers, notice, okay? So it's always, it always gives you, gives you a relatively large contribution because they don't have cancellations. There are no minus signs. The wave functions are just coming as the amplitude. And of course, you see you are integrating over all the R's, all space. So you're getting, of course, contributions mostly from ij that are close to each other, like nearest neighbor. But what is more important is to look at what kind of process is described by these coefficients. Because now let us see what operators come in. What is the process? So it's a process where you have, let me write this part, I want to call it V Hartree is a sum over I and j. Notice that there are only two indices for the position and two indices for the spins. And now I have this U Hartree ij, and the process is AI dagger sigma, AJ dagger sigma prime, AJ sigma prime, AI sigma. Okay? That's these are the processes. But now let me rewrite it, and you see that actually the U, this coefficient don't depend on the spin. So I can write it, yeah. Okay. Never mind. You find it in the notes. So okay. Sorry. So let us just reshuffle it. So what do we have here? We can write it as a sum over ij, uij Hartree, and now I'm doing the sum over, I'm deliberately reshuffling things, but without changing the results. Times the sum over sigma prime of aj sigma prime dagger aj sigma prime. Okay? You agree that this is actually the same? Actually, one thing I did here, I a bit cheated because in this form it's not in normal order. I reshuffled this guy here. Okay? And then maybe I'll have to subtract some vacuum expectation value, but I don't care, because what is this? Why is it convenient for me to write it like this? So this this is nothing but, sorry, it's not total n because it's only for a single I. So, but it's ni, so operator ni. Okay, I sum only on the sigma, and this is nj. Okay? So the Hartree part is actually very simple. I have some the number of electrons on site I, number of electrons on site j. It's just interaction between. Okay? Just think of it like this. I have so if both states are occupied, then I get some contribution, which is just a product of occupations. Okay? And in fact, this kind of interaction has a classical analog, because even if the electrons were not quantum particles, if I put two charged particles next to each other with some distance, there is an interaction between them, and it's a product of the densities. Okay? Okay? All right. So this is called Hartree, and usually these kind of interactions are the least interesting. The least interesting because they have a classical analog. But the more interesting one, I don't know if I will complete the 3, but at least the 2. The next one is called fork, the same fork of the fork states, fork or exchange. Okay, so what are the exchange terms? They are also special case of the choice for I prime, J prime, such that, again, they depend on two indices, but with reverse. So Uij, Ji. Sorry. Or, because they depend on two indices only, people give them a name. What is the name? So, again, this is standard in the literature. For some reason, the choice is to call it J. Not U, not V, but J. Why J? Where do you usually know?
Jump.
So, where do you usually see the letter J in relation to interaction? Maybe it's in the other advanced course. In spin, like in Heisenberg model and things like that.
J, הדבר הזה שקופץ שם, לפני ה-SISJ וכל זה, עם הגורם הזה של האינטראקציה בין שני.
Yeah, usually when you write spin interaction models, you use the letter J, and that's a hint that this kind of this choice of terms in the interaction, which is, I insist, comes from Coulomb interactions. It's not magnetic in origin in any way, but it actually plays a dominant role in magnetism. Okay? In fact, this is the way to get the Heisenberg model, the Ising model, all those comes from this kind of terms. So, what is special about it? I will not write the matrix element, it's not important, we can just plug it in. What I want to show is what kind of processes it describes. So it describes processes where, let me just copy it here. You have an electron, this is A dagger I sigma, A J dagger J sigma, sigma prime, okay? And now, this is the big difference. So, unlike here, so here we had the AJ dagger sigma prime and A also with the same quantum number. But now what am I doing? For each spin, I exchange the I and J of the last two operators. So it looks like this. And now you see that if I sum over all sigma prime, for example, I don't get a number operator, because for each spin, you get a hopping. This combination gives you hopping from I to J, and this from J to I. Or in other words, what is going on? If these are sites I and site J, the process described by each of these terms is a process where the particle with spin sigma prime is being annihilated from I and hopping to J. So this is sigma prime. Whereas the particle with spin sigma is going the other way. Okay? That's what it is, and that's why it's not so trivial. Because, and you see now why it's called exchange? Because it's a process where you take two particles with now, let's say, different colors. If they have different spins, you exchange them. Okay? Actually, even if they have the same spin, you can exchange them. You can exchange them, and if sigma equals to sigma prime, notice that you get a term, the special case, let me write it down, sigma, and if sigma equals sigma prime, I mean, when you have the double sum over sigma, sigma and sigma prime, you have either sigma equals sigma prime or sigma different, okay? If sigma equals sigma prime, from the Fock term, you get something that has the same sigma, but I goes to j and j goes to I, okay? So two identical particles are just exchanging between them. In the Hartree part, which is the direct, you also have a term with the same sigma, but that term, there's no hopping. You have a particle stays on I and another particle on j. Okay? Now, if you look at the two terms, let me write them down explicitly. So you get from the sigma equals sigma prime, you get one term from the Hartree that looks like this, I sigma, ij, ij, I sigma, right? From the Fock term, you get almost the same, but now the other two are exchanged.
And they cancel each other out.
Exactly, right. So, again, this term exists, okay? It's just one of those. This term exists, but what is the difference between them? A minus sign, right? Because in fact, this and this are the same if you apply the anti-commutators. You can exchange them and you get a minus sign, and then you're back to the Fock. Now, if you have both, right, both in the Hartree and in the Fock, you have the same term but with a different sign, it cancels. Okay? And that's very interesting. Why? Because, and notice, by the way, that why am I allowed to exchange them? There's no one. There's never a one. Or there's no, the anti-commutator is 0. Because I must be, for the exchange term, the I must be different from, sorry, for the same spin, the I must be different from j, otherwise it's 0, right? Because you cannot have the same indices, cannot have AI sigma squared, okay? So this is 0. Okay, so what does it mean, this phenomena that I just described? Let's say that the interaction is indeed coming from Coulomb interaction, which is repulsive, right? It's repulsive. And the Hartree term give you repulsion. But the electrons with the same spin feel a reduced repulsion.
All the spins are in one direction.
Because they are in one, so if they are in one direction, they feel the repulsion less. Because of that, the system will have a tendency to align the spins. Okay? So, because that's the thing, because the Pauli exclusion, because in a sense it forces electrons to avoid each other, this is a pictorial way of describing it, it reduces the effect of interaction. But only if they have the same spin flavor. Okay? Okay, so the result of this, that if you have repulsive interaction in cases where, okay, so you always have that, okay, in quite general, And in principle, you can, what does it give? What kind of effect it gives? It creates a tendency for ferromagnetism, because what is ferromagnetism? It's an interaction that tends to align the spins, okay? And you see that it's coming from the Coulomb interaction. It has no magnetic underlying principle. It's a combination of Coulomb interaction, repulsive, and Pauli principle. So it's really quantum effect, okay? And it would give you ferromagnetism, except it doesn't always give you that. Why? Because in many cases, if the kinetic energy is very large, it actually reduces this effect, and it's there, but it's small, okay? Actually, if you do perturbatively the interaction in a metal, it does give you some contribution that reduces the energy, okay? But if you have a material that is almost an insulator and the electrons have a very small kinetic energy, and they're really almost stuck on the sides, and the interaction is everything, you get a ferromagnet, okay? That's one way to get a ferromagnet, the simplest one, and there are some examples in nature where it's there. Okay? Not all the ferromagnets are coming from this. Actually, ferromagnetism in iron is much more complicated. It's also metallic, so it's much more complicated. But this effect exists. Okay, and there is a last term, maybe just mention it in, I take just 1 or 2 minutes to say what it is. And then we'll at least finish the classification. And that's called, in fact, it could be sort of the simplest one. It's an on-site, or sometimes called after Hubbard interaction. On-site. Okay, so this is the term where all the indices here are the same. Okay, U, I, which, because there's only one index, and in many cases it's in fact independent, because you have an ordered lattice, it's actually not even dependent on this index, and we just call it U. Okay?
But it does depend on the sigma.
I mean, just for, no, it never depends on the sigma. If
No,
it's a
but-
density interaction, right?
But it has to have different spins.
Of course. You still have summation over spins.
Yeah.
Of course, yes, exactly, right. So I'm getting it. I'm just saying that the coefficient, if you look at the expression for the matrix element, if the wave functions are really coming from a periodic lattice, it's not even dependent on I. Okay, so you can actually take it out of the sum and call it U. Okay, so this gives an interaction that we call So what is the interaction that it gives? Actually, let me call it the Hubbard or on-site. Okay. So this is how it looks. Now you can write it like this, and now you have a sum over sigma prime of you see all the the lattice indices are all the same, but you have different speeds, okay? Yes, no, just a minute. But now notice that what have I written here, actually? Let me rewrite it. So this is actually Ni up to normal ordering, okay? It's Ni sigma times Ni sigma prime. It's really on site, okay? So it's just the product of occupations of two electrons, one with spin sigma, one with sigma prime. Now, when you look at it, so in principle, the sum includes 4 terms. Sigma can be equal or different from sigma prime. But what happens if sigma equals sigma prime? It's 0. Why? Once again, it's just not there. It's a 0 identity. Yeah? Oh, sure. Yeah. You're right. I'm saying that if you look at the matrix element, and you also include another information, that the wave functions, because it's a periodic lattice, the wave function is the same function. Therefore, it's the same integral for all I. Okay, just look at the integral for yourself, and you discover it's not an important point. I'm just saying that it's true. Okay. What I want to point out is that because of the Pauli principle again, there is no contribution from sigma equal to sigma prime. And therefore, I can actually rewrite it in the following way. It's Ni up, Ni down. And that's it. You see, the factor of half disappeared because I accounted for 2 terms, that sigma is up and sigma prime is down, and vice versa. Okay? So this is the on-site interaction, and you can think of it as it's just a contact interaction between 2 electrons that have opposite spins, otherwise it's not allowed, and they sit on the same lattice. Okay? Just a minute, and lastly, this is just a notation. Now, if you write a Hamiltonian that has the following form, first term is minus t times nearest neighbor AI, AJ plus AJ dagger AI plus U times Ni up, Ni down. So this is a model where the H naught, the single body, one body term is just a hopping between nearest neighbor, like a tight binding. And the second is an on-site interaction. This is called Hubbard model. Okay? And it's a very, very, very useful model in solid state physics of strongly interacting materials, because in different limits, and especially in the regime where U is much larger than T, you can get all sorts of interesting phases, okay? So, in fact, you can get not ferromagnetism, but anti-ferromagnetism, for example. And why is that? You'll see it next week in the tutorial. But these 3 terms that I mentioned are the most important special interaction terms that have significance. And yeah.
Why? initially you do not divide u by ui when you define ui.
I don't divide what? Sorry?
When you define ui I,
Yeah?
why not divide by 2 u?
No, I'm saying this is the.
in initial.
Here I use the original definition, but because when I sum over sigma, I have up, down, down, up, down. I have 4 terms. 2 of them vanish, and the other 2 give me the same, right? Because both of them will give me this product is just the same. Okay?
כן, אבל
So I get twice the same thing, and it cancels the factor of 2. That's all.
לא היית צריכה לחלק מההתחלה ב2.
No, I did.
בהגדרה.
I did.
אוקיי.
Yes. It's the same factor of half we had by the time. בסדר? Okay. Thank you for the attention.
שאלה. נכון, יש גם אחד לקרוא מודל?
במודל הזה, אנחנו נגיע לזה.
אוקיי.
עוד אולי שיעור הבא.
טוב.
זה לא מודל,
משהו,
זה שיטת קירוב. זה בעצם סוג של קירוב.
אוקיי.
אז אנחנו נדבר על זה בשיעור הבא.